Hello, my name is Isaac Fortier, and I am the project lead for the OSHE Growbot team, and we will be presenting on the Growbot project. Team members consist of myself, Nick Redman, and David Hostetler. The Growbot has been designed to be an open source robotic platform for home gardening, specifically targeting those DIY enthusiasts who want to automate and streamline their gardening management. The robot platform is operated by a traditional compute system that controls two motors through the use of electronic speed controllers with encoder feedback. The drive system is powered by a 6S LiPo battery that is stepped down to 5 and 12 volts respectively for control power. An autonomous charging system is operated through our base station electronics with relays, an IR sensor, and an Arduino Nano to mitigate any safety concerns with providing voltage to our charging prongs. Charging of the battery on the bot is controlled via a battery management circuit directly connected to the terminals of the battery to prevent overcharge and overdischarge of the system.
To control Growbot, we are using the Robot operating system, which is a suite of open source robotics middleware. ROS allows us to quickly develop a control system for the bot that is reliable and modular. One of the primary features we are currently using is ROS Serial. It allows us to use an Arduino Mega or other microcontroller to abstract all of the analog and digital I/O away from the compute module. This allows for the use of compute modules that do not have onboard I/O headers. This is also how we are able to interface with our drivetrain and any sensors that we wish to add to the system. Using the point cloud library provided by ROS, we are also able to utilize the Connect V2 sensor to create 3D point maps of the environment around us. These maps are what allow us to navigate through the garden and allow us to identify plants and other points of interest.
The Growbot was designed in an open source CAD software known as FreeCAD. The frame of the robot is built using 3030 aluminum extrusion and held together with corner joints. This creates a sturdy skeleton to enclose the electronics and maintain a uniform center of mass. The axe assemblies are mainly custom 3D printed parts utilizing PETG, while the tires are printed using TPU filaments. This allows for dampening in the chassis and allows the user to make changes to the design of the tire tread to fit the desired terrain. This semester, we implemented an autonomous charging system to promote full autonomous operation. Additionally, we had a robot overhaul to add more space and extend the wheelbase for added stability and more clearance.
My name is Nick Withman, and I did 3D printing hardware for my senior design. So what is BREAD? It's basically a modular data acquisition and control system aimed at garage and regular scientists, just so people can piecewise different systems they've made together. And it was originally developed by Dr. Oberleuer over the summer. The overall goal for me was to create the necessary hardware for BREAD to control a 3D printer. So this semester, my results of that are the heating slice, the buck converter slice, the thermal reading slice, and the stepper slice. The latter two I mainly worked on over the summer when I was working with Dr. Oberleuer. So first, the heating slice, there's the schematic of it. It just controls the heaters on the 3D printer. This is a second iteration of one I made. The old one I made didn't work as well as this. It's over-engineered for safety. There's a bunch of different feedback paths. There's a fuse in there. There's a redundant screw terminal so that there can be a safety switch implemented if people want. This was mainly designed for safety and complete understanding of what's going on and just general choice of how to implement things in an end user. The buck converter slice, this one was made to power down an already existing 24 volt power supply on the 3D printer, and it was just a nice ubiquitous thing to have. It's supposed to be very simple, easy to look at, as you can see there, and it can also function as an inverter, although it's only a half bridge. So it has a little bit of utility to it. The thermal slice that I mainly designed over the summer, I did some edits to it this semester to make it a little bit more SBI friendly. And it's had some issues with the type of chip we originally used, so we've re-implemented the fix to that when we because we reuse that circuit that you see repeated there a lot, so we just re-implement that the correct way now. And here's the stepper slice that we made over the summer. This is pretty integral in getting the 3D printer to work because it, the motion is controlled by stepper motors, and basically all it is just some plug-in stepper controllers controlled by the central Arduino there and some feedback. And that's it.
Hello, my name is Ian Huff, and this video is about my project submission for the Design Expo, a text-to-speech slice for the Bread family of circuit boards. A little bit of background about my project. The goal is to create a bread slice that receives text input and produces speech audio. And so during the initial design, the options were to either purchase a dedicated IC chip for the text-to-speech or just use a Raspberry Pi. I found an open source library online called eSpeak, and it allows Linux machines to produce audio data from text. And this, in combination with the text-to-speech chips being unavailable just about everywhere, led me to choose the Raspberry Pi option. And it's important that in my design, the project is consistent and compatible with existing bread standards and slices. The plan for my system at the end of development will have the finished product look like this. These blocks in the middle are the parts that will be on the physical board. These are the Arduino Nano that is standard on every slice, and a Raspberry Pi Zero for the audio generation, and these two will communicate using their USB ports. The board takes in data via I2C communications and outputs data to a speaker. This semester, I've created a mock-up system that allows me to simulate the functionality. I was unable to secure a Raspberry Pi Zero due to the chip shortage, so you'll notice that I'm using an older model Pi, and this device doubles as both the onboard Pi and the external data source in my mock-up. The audio is also currently sent via the headphone jack in my mock-up rather than the pinouts. Here's a picture of my mock-up in its current state. The Pi is running software that takes keyboard input, sends it to the Arduino over I2C, and then waits to receive data over serial communications. You can see the 3 jumper wires connecting the Pi and the Arduino, which allow the devices to communicate using I2C. The USB cable then sends the data back to the Pi, which uses eSpeak to generate audio and play it on my big JBL speaker there. And here I have a video that shows my mock-up in action.
This is a test. Testing, 1, 2, 3. According to all known laws of aviation.
Hi guys, my name is Nikki and this is my senior capstone project. This is the blood glucose meter, and here I am joined by Etienne and David. So the point of this project is to create an open source blood glucose meter. Initially it was designed from an old blood glucose meter in order to take test strips, test a sample of blood, and then measure the glucose levels. However, we did run into issues which will be talked about later, but we decided to kind of reconfigure our process of which we wanted to go about doing this, and we decided to kind of go the printing route. So in order to do that, we decided to take a actual laser printer and take a bunch of chemicals that we ended up ordering online and printing different layers of them. With that, we're going to be taking a control solution and a regular solution using a spectroscopy measurement tool in order to determine the sources of light running through the blood in order to measure the glucose levels.
So throughout the semester, I've been working on designing a circuit to analyze the colors in the test strip and figure out what the person's blood glucose is based on that. I found a very fancy IC that detects UV light and found out that the chemicals will change their absorbance in the UV spectrum when they are exposed to glucose and the blood. So we picked up the IC and have been working on reading it with a Arduino-based board. And I have a first iteration circuit right here. And I'm working right now on creating the final version that is soldered together on a PCB.
So in the first half of the project, we ran into issues with the copyright behind the test strips used in commercial glucose meters. They're an amperiodic method using glucose oxidase, but they've got a proprietary connector which we couldn't find, and we couldn't reverse engineer without running into legal issues. So the original idea of making a system that worked with existing test strips fell through. So instead we switched to using a colorimetric based system, similar to the old style of glucose test strips where they just dipped it in and then analyzed by looking at the color. We found a paper that involved printing using the chemicals onto our own strip, then analyzing it using pass-through colorimetry. We've ran into multiple issues on this end too. First of all, printing the strips, we've had issues with the printer itself, with the old ink cartridges and clearing them out. We've also had issues with the chemicals in that they took the entire semester to turn up, meaning that we were significantly behind schedule. We're now having issues with storing the chemicals once they're back in liquid form, as they need to be stored at negative 20 degrees Celsius, and actually printing them due to issues with the heating of the printer.
So up next you'll see a video of us printing with our printer, testing the different levels of liquid in which we can put out of the sponges. And now you will be seeing a video of the 3D printer for our lid to the ink cartridge. And so to wrap up our project, we are continuing to work on the testing of our strips using various porous papers and our printer, and looking to see how our project will end up this semester.
Open source hardware enterprise near field audio speaker. The purpose of this project is to create an open source wireless speaker leveraging near field technology. Some of the advantages a device like this has is it's low cost, it's energy efficient, doesn't require any signal transmission from the device, it's easy to implement, and it's easy to use. Places this could be useful are cars, and like my design, portable speaker. The external design is made to be resonant resistant, easy to print, and easy to assemble. The internal design has audio and power delivery physically separated, and variable receiver height support for any sort of device to be compatible. Some of the roadblocks I've had: lack of information about near field technology, headphone output proving to be pretty much impossible, and just in general 3D printing. Some of the features you can see here are polyfill to add greater depth to the sound in such a small enclosure, the custom wound copper coil receiver to pick up the intended audio input without much noise, the bronze infused 3D printing material to again reduce the resonance, and the 3.5mm stereo input.